Good afternoon, everyone. Welcome to another riveting episode of Dave Does Math from Home. Today we're talking about limits. And the entirety of Chapter 2 is about limits. This is the first section we're covering, 2.2. We're skipping 2.1. We're going straight into 2.2 to talk about limits. And before we get into the specific content of 2.2, we should talk a little bit about what limits mean and what they're for, and what we're going to do with them. So, when I was in high school, my calculus teacher defined, or maybe he described, I don't know what the difference is in this case, he said that calculus is the study of the infinite and the infinitesimal. And at the time I believed him. At this point I think I know enough about calculus to disagree with him, but he's not entirely wrong. Calculus has an enormous amount to do with the infinite and the infinitesimal, as he says. These are tools that we're going to use. Infinite and infinitesimal things are sort of like the foundation that calculus is built on. The problem with that is that they are very, very nebulous, vague, sort of hand-wavy ideas. They don't make a very good foundation for a scientific field of study, which is going to be a big problem for us. We want to be relatively confident that calculus works. And if we're confident that something works, we don't want it built on a vague sort of have-to-find notion of infinity as something that's really, really big, or infinitesimal as something that's really, really, really small. So small that you can't measure it. Well, doesn't that mean it's zero? It's not a good foundation for science. So, what mathematicians did to sort of solve this problem that they created for themselves is they invented limits. And limits is a very formal, official, well-defined way of doing fake mathematics. That's what they're for. That's what we're using them for. We're not ever actually going to study anything that's infinite, or we're not ever actually going to study anything that's infinitesimal. We're going to use limits to pretend like we are doing that while never actually saying that we're doing that, which is a huge distinction. So, limits is how we're going to sort of get around this idea. So let's talk about what limits are. The first thing we're going to talk about is a limit graphically. So visually, if you're looking at a graph, you want to know what the limit of something is. Limit means what the function looks like it's doing. So already the sort of fake maskness of this is already shining through pretty spectacularly. This is what a limit means. It's what the function looks like it's doing. So I have here a graph. It is kind of a mess. There's a bunch of pieces missing. It's all kind of disjointed. But it is a function. It passes the vertical line test. I don't know what the equation you would use to create something like this. I could probably figure it out if I had enough time. It would definitely be a piecewise thing with like a linear piece from -4 to 0, and this is a quadratic piece from 0 to 2, and then a constant piece from 2 to 4. We could figure out the equation for this function given enough time. I kind of don't care what the equation is. Right now all I really want to investigate is the limits of this function at various points. Maybe I should add that. What a function looks like it's doing at a point. So, let's start by figuring out what this function looks like it's doing. We'll start with a really easy one. I want to know what this function looks like it's doing when x is 3. So here's 1, 2, 3. At x is 3, this function looks like it's doing this constant bit. This constant bit looks like it's y equals -2. So I'm confident in saying that the limit when x is 3 is -2. So it's like a y value. And in this case, it does equal the actual function value. The actual y value here is -2, which is one of the most important things you can sort of realize about limits, is that a lot of the time, what the function looks like it's doing is exactly the same as what the function is actually doing. That's going to happen a lot. Here, the function looks like it's -2, and it is actually -2, and that's great. There's no conflict there. The function can look like it's going to be -2, and it can actually be -2, and that is fine. That is okay. That's going to happen a lot. We can do the same thing back here. If we wanted to look at the limit when x was, let's say x is -3. That's this point right here. When x is -3, the function looks like it's going to be 1, and it is 1. It's perfect. We need to talk about notation while we're doing this. So right now we have this x equals -3 and this x equals 3 piece. So let's pause here and talk about notation. When we're writing these limits, we should write the limit as x approaches 3 of f of x is -2. So the limit is the y value it looks like it's going to be. The limit as x approaches -3 of f of x, that's +1. The limit is the y value the function looks like it's going to be. It's interesting to note in these two cases, f of 3 is also -2. F of -3 is 1. So if you want f of 3 or f of -3, these are actual function values. This means what the function is actually doing at these two x values. And at x equals 3, the function is -2. When x is -3, the function is +1. That's fine. So these are actual function values. These are the limits. Now it's time to look at what happens when these things don't agree. And for that, I want to look at this point right here. So this is x equals 1. And I want to talk about the limit as x approaches 1 of f of x. So this is an interesting case because we have an open circle here, and we have a closed dot here. So I also want to eventually talk about f of 1. So I have f of 1, this is the actual function value at 1. And I have the limit as x approaches 1. This is what it looks like it's doing. What it looks like it's doing here is it looks like it should be getting to 1. That's what it looks like. That's these if you follow these lines towards 1, that's kind of what these approaches mean. There's a lot of imagery and metaphor of motion sort of embedded in this idea of limits. If you think about moving along this path towards x equals 1 from both directions, it's going to look like you're going to this y value, y equals 1. So that's what it looks like it's doing, and that's why the limit is 1. What it's actually doing is this closed dot down here. So the actual function value is -1. So this is where we're getting into the sort of fake math thing. The actual function value is -1 because that's where we get the closed dot. If we're talking about a limit, then we don't care what the actual function value is. Like sometimes they match and that's fine. That's a nice coincidence, but we kind of don't care whether or not they match. That's not a huge deal. Sometimes they don't match. And so we have two different ways to talk about what's happening here. In this one, This is what is actually happening at that point. And what's actually happening is we're down here at -1. Here we're talking about what looks like is happening. And that's right here. It looks like it's going to +1. This is the fake math bit, which is fine. We're all about fake math here in calculus. So, I think that's the only really interesting point here that we can talk about right now. That's not true at all. Let's talk about more of these things. Let's talk about the limit as x approaches 2 of f of x. And while we're at it, let's also talk about f of 2. So 2 is going to be right here, which is going to be really awkward for us in talking about a limit. We can talk about the function value very easily. If we want the actual function value, what the function is actually doing when x is exactly 2, we just have to look and see where the dot is. We have a dot right here, and that's fine. So it should be 4, I guess. F of 2 is 4. Great, perfect. That was easy. But what does the function look like it's doing? This is going to cause us some problems, because this is where we're going to get like 2 different answers. Right? Like, on this side, the function looks like it's going to be 4. And on this side, the function looks like it's going to be -2. And it can't be both. One of the most important things we talked about in pre-calculus was the definition of a function was very clear that every input gave you exactly one output. So we have one input and we have exactly one output. F of 2 is definitely 4. There's no other possibilities. There's no other options. We want that to be true of limits as well. We don't want to have to say that the limit as x approaches 2 is maybe 4 or maybe -2, depending on how you're feeling this day. It can't be 2 different things. Because these things don't match, in this case, we say that the limit does not exist. But wait, there's more. Saying that the limit does not exist is kind of a problem, because we do want to be able to use this idea of limits even when things don't match. So we're going to sort of fine-tune this idea of limit a little bit to help us out. I'm going to say the limit as x approaches 2, if I put a little plus here, sort of like as an exponent on top of the 2, this plus means from the right. So now x equals 2 is here. And if I use this little plus, I don't care what's happening to the left at all. This is meaningless to me. I'm going to cover it up. It doesn't do anything. I'm only looking at what is happening as x goes to 2 from the right. So I'm only looking at this part of the line here. And in this part of the line, the limit is -2. Because I've only got one sort of input here. It's very clear. This is a constant -2, so that's the limit. I could also look at the limit as x approaches 2 from the left. If I put a little negative sign here as like an exponent on top of this 2, that means that I'm going to completely ignore this. Everything to the right of this line is no longer important to me. I'm only looking at what's happening to the left of 2. And to the left of 2, this function looks like it's going towards 4. These are called directional limits. And one of the things that's very important about directional limits is that this thing, the neutral limit, Neutral means sort of non-directional. If there's no plus or minus, that means it's neutral. And that means both directions. And the neutral limit, for the neutral limit to exist, both of the directional limits have to exist and they have to agree. So in this case we have two directional limits. They both exist. I get numbers for both of these expressions, but they don't agree. One of them is 4, one of them is -2. If they can't agree, then the neutral limit doesn't exist, which is why we have a DNE here. We could talk about limits of other numbers. Like we could go back here to -4. If I want to talk about the limit as x approaches -4 of f of x, I'm going to first talk about the limit as x approaches -4 from the right, and then I'm going to talk about the limit as x approaches -4 from the left, and we'll see what happens. From the right, I'm only looking at stuff that happens in this direction, and in this direction it looks like it's headed towards 0. So I'll pretty confidently say that the limit of f of x as x approaches -4 from the right is 0. From the left, I'm kind of out of luck. Like there's no function to the left of this. This just ends at 4 pretty abruptly. There's nothing else back here. So it doesn't look like the function is doing anything to the left of 4 because there is no function to the left of 4. So we'll say this does not exist. And like I said earlier, if we want to have a neutral limit, then both directional limits have to exist and they have to agree. One of these directional limits does not exist. That means the neutral limit doesn't exist. Also, the function value, if I just want to find out f of -4, that also doesn't exist. This is an open dot here, back at -4, which means it looks like it's going towards -4, but it doesn't actually get to -4. There's no dot anywhere here for x equals -4. So this thing also does not exist. -4 is not a very fruitful source of information for this function. We tried 4 different things here, and only one of them exists. But one of them does exist, which is part of why limits are so important to calculus. It gives us a way to talk about what the function is doing when the function doesn't exist, which is what we really need moving forward. So the actual function doesn't exist. The neutral limit doesn't exist because the limit from the left doesn't exist. But despite all of that, we can still talk about the directional limit from the right. That's 0. So this is a sort of analytical way to describe what the function is doing in weird spaces wherein it's doing weird things. I'm now pretty comfortable sort of flying through some of the rest of this. The limit as x approaches 0 from the right should be 0. The limit as x approaches 0